All right. Our next speaker is Curt, all the way from University of Hawaii. Yeah.
All right. You hear me all right? I can hear that it's on. Aloha from Hawaii. I have the unenviable position of being between all of you in the end of the conference. And I hope you'll indulge me. I pivoted my talk just a little bit, I think, to make it a little bit more relevant. But I will talk a little bit about NDP. First, I'm going to start I guess a little bit about me. I'm a software engineer by background. I work at the University of Hawaii, the Institute for Astronomy. I manage a team of IT sysadmins and help desk that supports our astronomers. Is there laser pointer, yeah. And so, one of the things I do is science data integration with Open Science Grid, NRP, and Open Science Data Federation. So this is something I'm interested in. Last year was my first time at HTC. I love this community. I think it's just fantastic, and I'm trying to figure out how we can use what you do more. Last year, this will surprise no one, Marone gave me some homework. And he asked me to identify an end-to-end use case using OSDF to stage data to OSPool or NRP or something for computing. And so I'm going to walk you through my experience working on that. I'm part of a research group that's doing spectropolarimetry and AI for the DKIS telescope, which is the world's largest solar telescope. It's on Haleakala in Maui. And our objective is to develop deep convolutional neural networks to estimate what's happening in the sun's atmosphere for observations that are coming from this telescope. And so to do this, we ran 2 million core hours on the Cheyenne supercomputer in Wyoming that simulate the sun's atmosphere. And then we took those simulations, and for each time step, we simulated what an observation of that would look like, kind of through the telescope instrument. And then using this pair of what you see and what's happening, we can train an AI model. So here on the left is kind of an example of an image that you might get of the sun through the telescope. And then to the right are some slices of the solar atmosphere that would correspond to that image.
For the simulation, because it's going to be related to my final comments, is what's involved in running a single simulation?
Yeah, in this case, it's an MPI kind of HPC simulation.
So how many nodes? How many roughly? Is it 10 nodes, 100 nodes, 1,000 nodes, a million nodes?
It was hundreds of nodes, I believe.
Hundreds of nodes, one simulation.
That's right. 6 initial conditions. So we ran our simulation 6 times from a given initial condition. So effectively.
And how many simulations did you run?
6.
6
separate simulations, yeah.
And then what did you use for your training? The time steps or?
Yes. Yeah. So then we take snapshots every 40 seconds in the simulation time.
So as far as the training, each snapshot was a data point.
Yeah, right. Yeah. So, and we haven't even gotten to the time series in terms of our AI modeling yet. We're just doing static AI. So just given one frame.
And how many snapshots did you have roughly?
I don't have the number handy. But
hundreds of thousands
or
millions.
Tens of thousands to hundreds, maybe hundreds of thousands.
Okay, thank you.
Yeah, it's very large scale, 130 terabytes total.
Yeah, I'm interested in the numbers. Okay, thank you.
And I guess again, what we're trying to do is go from the left picture to the right picture, right? Okay, so this is kind of my journey, right, of using OSDF to publish this data set. So we ran our simulation, it produced some files. We use those files for a second step, which is synthesis, which, by the way, the synthesis step would run this is a high throughput step. So we could have done this on the supercomputer and then used HTC to do this. And there's an opportunity going forward in this space for us that I think is very interesting. Then once we have all of, once we have all of this data, and this is actually incorrect because DR1 is our data release one. So this is all of our data. We used Globus to transfer it to Hawaii from Wyoming to our project storage. Okay, and then here we split out our initial data release for our first publication. So we wanted to have data that comes with our paper. And the paper just describes the simulation, the process that we used to create all this data. We took that data, we exposed it as a Globus collection. So you can use Globus to download our data. We exposed it on a data transfer node using HTML, we're using a web server, so you can just use curl to get it. But we also wanted to use OSDF, and so we exposed it as an origin. And that actually involved an explicit put with Pelican to move the data from project storage into our data origin storage, which was part of a CC star. So
as far as I'm concerned, an origin doesn't have storage. So you had another object store.
Correct.
That you moved, and then on front of this you put an origin.
That's correct. Right.
Okay, and you did the movement from this storage
right
to
that. Yes.
To that storage.
From this storage
to this storage that had in front of it an origin.
An origin. It has a namespace, right?
Yeah, I understand. But I also want to make sure that we don't talk about putting data in an origin, because an origin is an interface in the same way that you expose it via Globus. You created another object store.
Sure. Right. And I think that's something I want to talk about a little more. We also created a Jupyter notebook to release with our publication so that specifically the notebook walks the user through using each of these methods to access the data. So there's a section of using Pelican to pull the data from an origin, right, or using the namespace, using the URL, how to use Globus to pull the data, how to use curl to pull the data. And then there's a visualization. So once you've pulled the data into the notebook, you go through and you can visualize and experiment with the data a little bit. So this is just a small sample, maybe 15 gigabytes of data in this sample that the notebook utilizes.
Prevented you from, why did you need another storage? Why couldn't you, what you call expose, why couldn't you expose via an origin like you expose like Globus?
There's no reason that we couldn't just put a Pelican service running on this data transfer node, just like we do Globus, and expose the bits directly. There's no reason. Yeah. Okay. So what is the reason? Because we wrote it into a CC star.
Yeah, I understand the politics.
And then we needed a science use case to use that storage so that it goes in our annual report. That's
okay.
Okay. Anyway, so now we have these three ways of getting to our data. We have our notebook. We have, of course, our paper, and now we wanted to give people a way to find that data. And so we used National Data Platform, which is kind of working on this data discovery and so on, to register each of these, including a link to our notebook in NDP. And then I came here and saw that Brian and his team had kind of created a page that lists OSDF origin URLs. So it turns out that someone registered our data set for us on OSDF. Okay, so here's the National Data Platform registry. So you could see kind of from a user perspective, I could tell a solar astronomer, go here, and you can go here to get to our data. And then here's our entry here on OSDF's list. And here's a quick look at our notebook. running in an OS, in a notebook, running on OS pool. But I'll comment, I kind of made a comment yesterday. There's a plethora of sources for data, and it's a long list. And so I think this is a problem, and I'll circle back to kind of this issue. I'm going to jump into a different issue. I'm just going to kind of talk briefly about access patterns for astronomy data, which I talked a little bit about last year. I'm going to go pretty quickly. You have this interactive search and download. So you go to a web page and you can type in a query and you can get some data, and then you kind of maybe can look at it. So kind of a data portal. And the typical astronomy archives have some kind of a capability for that. I'm not really going to say anything more about it because it's not scalable for using, OS pool or something. Bulk download by arrangement. I'm going to talk a little horror story about that. But basically, I can reach out to the astronomy archive. I can contact somebody and say, "Hey, help me get my data." There's various Pythonic APIs or scripted APIs that you can use to get to your data and write a script, basically. They're slow. They don't scale very well. And increasingly now we're seeing the use of cloud, Amazon, for dropping large amounts of objects, and then private clouds, and I'll talk a little bit about that, and then two kind of concepts of, well, how do you get to the data in these private clouds? Okay, so just real quickly, here's my experience with the bulk download. Like, okay, I can't get at the data, but I do know this guy, Bernie, who works at the archive, and I'm going to ask him to prepare like a way for me to download the 600 terabytes of data that I need, which, by the way, at a gigabit takes 55 days. I get back a tarball of almost 2,000 scripts, each with 2,800 curl commands. Oh my gosh, I figure out how to script all this. And then I get pulled away. It's a two-stage copy. I get pulled away by other things on my plate. The PI finally gets frustrated and is like, "Curt, go explain to a grad student how this works so they can finish the work," right? And this took months. It's not a way to do things. Okay, you got the scripted search. Like here's an example kind of on the help page of like, okay, we're going to take 15 observations, right? So we're going to go to a point in the sky, an object in the sky. We're going to look at it 15 different times. Okay, and now we're going to take all the combined observations of those 15 observations. We end up with 6,700 files, 300 gig. And again, lots of warnings about be careful about how you download this 300 gig. Good luck, figure it out, be careful, proceed cautious. It's not an effective way of getting to the data. Okay, this is getting better now, right? So actually Space Telescope, to their credit, they're like, you know what, we're gonna start using AWS. We're gonna start pushing data out there. We're gonna start providing services there. Okay, so here's a collection of, going back to my point about data's just all over the place. Okay, well, the Space Telescope Science Institute has a nice little page of their open data on AWS with some data sets. Unfortunately, you use their API and you're stuck back in this, well, how do I download the data from AWS to my local environment? It's slow and it doesn't scale. Okay, so what's better? Well, Rubin is, deploying their own Rubin Science platform where they're deploying data services and notebooks adjacent to the data at Slack. And we have a project in Hawaii that's taken this approach. They look at supernovae, variable stars. And so they run a service where you can directly interact efficiently with large amounts of data. So Rubin, Sky Patrol. Okay, then Rubin has this concept of a data broker, pub-sub model, right? So you say, I'm interested in these events. This is really for event-driven things. Time domain, a supernovae goes up, an asteroid's detected, something moved. You get notified. A quick note about NDP, they do offer kind of a way of doing this with your local data. So you could implement a data broker using the NDP endpoint. I haven't really seen this model kind of expressed in the Pelican for event-driven pub-sub. Here's a quick slide just about National Data Platform Endpoint. The idea is I can deploy it on-premise next to my data. We're working on getting it working in Kubernetes with their team. It runs this CCAN data portal, which is an open source data portal, and it registers the data back to the central NDP registry. And it offers this Kafka streaming, and it offers a Jupyter hub. What doesn't offer a Pelican origin, and that strikes me as odd. I think there's an opportunity there. And then finally, we have the virtuous OSDF model of Netflix for Science, which I'm a big fan of. Okay, so my takeaways from this year are in the form of some challenges for me, but maybe for some of you as well. I think that I mentioned data discovery. I think there's an opportunity for Pelican to leverage to not solve the data discovery problem and worry about moving data and what Justin just talked to us about, efficiently managing caches and all that sort of thing. But I think there's an opportunity to work more closely with National Data Platform to solve this data discovery balkanization problem. And so why wouldn't NDP have the explicit Pelican URL that I need for my data set, like built into it? Like they should just expect every data set that's registered to offer a Pelican. And going back to the NDP endpoint, if I'm deploying that for my local data, it should implement a Pelican origin so that my registered data exposes that Pelican URL to the end user. And then NDP is working on providing notebooks and courseware. And I think there's an opportunity for them to use, they're mostly using NRP right now, but I think they could run their notebooks on.
So that does NDP have the notion of different namespaces? Because when you go to NDP and you say, I want this piece of the sky, whatever, it comes back to you with object names.
Yeah,
so can you say, I want the object name in the OSDF namespace versus the namespace in the NASA namespace?
Right now, it doesn't make any assumptions, so it's just a big bag of reference of URLs, of links, and there's no structuring to it. And
so it will give you both URLs. It will say, if you go to NDP and you say, I want this part of the sky, it will say, here's a list of URLs for this one object.
Right. So I guess maybe it doesn't do that because it's not astronomy specific. But if I had a data set that was for one particular object, yes, I could list different links for different ways of accessing it. Got two other challenges. The other I just want to comment quickly is we heard discussion about using GPUs in OS Pool and AI machine learning, high throughput kinds of tasks. And I would just observe that hyperparameter search is a great opportunity for OS Pool to provide GPUs to solve. Ablation studies. So the idea of often when you're working with an AI model, you may want to say, if I take out this little piece of my model, how does its performance suffer? And you'll end up publishing a table that says kind of this component of the model contributes this much of the accuracy, and this component, this much of the accuracy. That's an ablation study. And that's something that can be easily partitioned into many parallel jobs that don't depend on each other. And then I would observe that batch inference. And so DeepSeek certainly underscored, and agentic AI underscores that you may have an initial prompt that goes to a large language model that then gets distributed into many subsequent inference predictions. And the need to batch those and efficiently process them is something that I think the OS Pool could be providing. And then I want to plug this concept of, which I've bent Brian's ear about. I think that Pelican subsetting and streaming. So I just experimenting. I ran my little notebook for our data, and it took about an hour and a half on Google Colab to download with Pelican the data. Okay, but there's no good reason. What my notebook's going to do is it's going to go and take little slices and it's going to explore it's going to open up the header, the metadata of the HDF5 file and interact with it. There's no reason that I shouldn't have an abstraction that allows my notebook to just directly talk to a service that's by my data that says, open this file and give me the result, or open this file, take this slice and return just that slice of data. And for machine learning applications, maybe a richer description of take this subset of the data and then partition it into threads, workers, and stream it out in some kind of a streaming, so that I can start. This solves, I think somebody showed us in blue, right, the wait time at the beginning of their jobs that was waiting for data transfer. And I think you could start processing as soon as the Condor job launches if you had this kind of streaming interface. And then finally, teaching in the CC Star meeting, we talked about the opportunities for driving education. And I really do think, and so I got a new challenge from Marone, really, which is, he said, look, you put a monkey at the top and the others will follow, was his metaphor. And I have to find myself an instructor monkey who wants to teach with using Jupyter notebooks. So that's what I have. I'm really interested in feedback and comments about some of these.
Any questions for Curt? Got several.
Just a comment. So if you have a 1 GB file and you want a 10 MB slice of it, that subsetting, I don't think is a Pelican problem. It's a problem with the file format. It's if you move from HDF5 to some more cloud optimized format like ZAR or Kerchunk, then it organizes all the metadata in one place, so you can get to whatever chunk you want.
Right. Yeah, it's similarly. I'm not from the high energy particle physics community, so I know that XRootD has some kind of built-in partitioning capabilities. I guess I'm looking through an astronomy lens, and we're somewhat immature. I think we've been doing astronomy for a long time. LHC was very much built with large-scale data processing in mind. They knew that's what they would be doing.
Go ahead, Brian.
So a couple pieces of good news in terms of one, some of your thoughts on NDP or either things that exist or kind of in the test version. So particularly along the lines of getting a Pelican URL indexed,
right,
or having a data set that points at Pelican. So
I saw that on their roadmap. I didn't see it in what I was watching.
I can connect you with some folks that know that. I really like your idea of being able to publish a existing NDP endpoint into a data federation. Right. That's not something we had put on the to-do list, but I think I'm going to pencil that one in.
Right.
Right. Particularly if NDP has the storage and they just want to make it available. I think that's one that would work well.
Let me just jump in real quick, circling back to Marone's question, right? Like, why didn't you just expose the data where it sits? Why did you copy it into some other place and then expose? Well, if I had my endpoint, that's exactly what I want to do with the endpoint, is run that on my data transfer node. And if it has Pelican origin built in, then I'm done.
Yeah, I mean, I have more question, because if you do you expose, are you concerned about the load that these exposed access capabilities generate on your object store? And one of the things that we would like the origin to provide you is some control over how much load, because you're looking at how long it takes you to get the data into your notebook. What happens if you have a class of 300 students, and all of them opening the notebook, and all of them are coming to your object store and say, give me the same object, and they take down your object store? You will not be happy. And now you have Globus, and you have HTTP, and you have an origin, and all of them come to do a denial of service on your object store.
And ideally, right, I would prefer not to expose the HTTP and the Globus. I would like to expose only the OSDF because of the caching that it does, right? I want to leverage
and because it can control, because you
Because of
can
the-
say, don't request more than X object per hour.
And going back to Justin's presentation, right? It's like if Pelican's implementing policies that allow a class to pre-stage an area and then efficiently cache my data from the origin into that, like that's the elegant solution.
This is the reuse. Now, you can also imagine if your object store is in the cloud, now you're getting into saving on egress.
Maybe the final point or challenge, you mentioned things like being able to only pull in objects as you go, or not having to pull everything
Right.
immediately. The counterbalance to that, the tricky part is we're really worried about how do we know when there was a problem in the middle of the job caused by OSDF, right? So if you think of something like machine learning training, we know you can start when the first byte of data is there, and you don't have to wait to start until we've moved all the data in. But what we're really scared of is, there was something went bump, 50 gigabytes in, or 5 bytes in,
Right.
and you didn't have a good error handling, and now your job crashed, and we can't help you. So that's.
And
There are ways to tackle that, but that's kind of where we're worried about.
I think, a separation of concerns, it might be that it's better to implement this streaming kind of thing in the NDP endpoint and let them solve that, right? As opposed to Pelican solving that. Maybe that's out of scope for Pelican. But I think I heard someone else ask for it, right? There's general utility for a particular data set size, right? Where frankly, an in-memory copy and no disk caching is virtuous.
Any other questions? If not, let's give Curt a final round.
Thank you. Thank you.